Well, thanks everybody. I hope you enjoy this. What I'm going to talk about is what's going on in the Linux networking community, because it's not always obvious. I don't think you guys follow mailing lists with 300 messages a day and go to 4 conferences and talk to people, and it's pretty hard to keep up. And that's pretty normal. That's a normal sign of a healthy community. It's lots and lots of activity. So there's some, and putting this talk together, the hardest part was choosing what to put in. It's not finding things, it's choosing what to put in. So first of all, as Greg Crow-Hartman likes to say, the Linux kernel is one of the biggest software projects ever done in the universe that we know of. 14 million lines of code right now. And it takes a while to actually run that program to find that. And drivers make up 9.2 million lines of code in the kernel. So the largest part of the Linux kernel is all the drivers. And I've done this myself. There's 393 network drivers, which make up about 2 million lines of code. So significant portion of those drivers are networking, but not all. And if you make a change to one API, you end up changing 393 drivers. That is kind of a roadblock, but it also is important to realize that there are changes that will be made like that. So if you have some out-of-tree driver, tough luck. If you have an in-tree driver and there's 394 drivers, it will get changed. And the actual core networking layer that does all the protocols and all the real work, it's pretty small comparatively, 6.7 thousand lines of code. So the actual core, one could argue that it's almost like the networking is almost like a microkernel compared to the amount of drivers that are around. It's important to realize that there are multiple users of the networking stack. It's not just the Linux desktop anymore. The first big user are all your cloud providers, Amazon, Facebook, Google, and even Microsoft has services running on Linux. And this is probably the biggest contributor right now, is the cloud providers, because they obviously have the most machines and the most usage. Phones, your Android phone runs Linux, everybody knows that. All your customer equipment. There's a lot of customer equipment out there that runs OpenWRT or variants thereof, whether legally licensed with GPL or not. And Google Home and Amazon Echo both run Linux. So your home devices also have networking. And the carrier backbones, a lot of the companies, even though they're proprietary, use Linux in one form or another. So it's actually a very wide universe. And it's kind of important because that kind of influences where we're going. The first thing is to realize the core set of networking developers is really a pretty small set. This was taken actually this summer at a meeting in Sevilla. And this is an invite-only group for the very small. There's like 20 people, and then there's a slightly bigger conference at the same time. But the number of people actually doing this is not, IBM or all of Google. It's a very small set of people. And the first question, the real motivation behind all this is, can Linux be used to cut your costs? Everybody is doing it, not out of the goodness of their heart. They're doing it. Can they do it to cut the cost of networking? We've all seen how Linux has cut the cost of server computing. Can Linux cut the cost of networking? And the first recent trend on that is white box. Who in this room knows what I mean when I say white box? Okay, so I'll give a, white box is basically, traditionally you went to Cisco or Juniper or somebody and you bought a proprietary thing that was built on proprietary silicon that the vendor designed everything, had a proprietary OS and proprietary apps. The first change that happened was it became really hard to do this silicon, just like almost nobody does their own custom processors anymore. So almost all the network providers are getting their silicon from companies in Taiwan. And they're actually getting like rack systems from companies in Taiwan. So then a bunch of other companies started to say, hey, can we take this commodity silicon and build a stack that uses open source components to provide networking gear? And it's called the white box, trying to be as generic. Like if you go to the grocery store, you buy a white box of cereal and it says oatmeal. And the way they use Linux in these environments is they use Linux as the OS to drive things, and then they mirror that change down to network switches. So in a traditional server, you have network cards in the rack, in the backplane, and in a white box switch, those cards in the backplane are replaced by an actual silicon switch, and there's infrastructure components to cause the network configuration to be pushed down to the hardware. This is done in many different ways. I think this picture actually came from Cumulus, and they were showing how they use, they're one of the vendors, but many other vendors are doing it in different forms to control white box switches. And how does this impact Linux? Well, all the APIs in here that need to deal with abstracting a network switch component are growing. There's several different implementations. The one that's being the most infrastructure based and kind of getting the most traction is the switch dev API, and that's growing. The early ones were all based off taking the Linux kernel and listening to what events happen. So as soon as you do that, you start to say, okay, well, I've got a backbone infrastructure of Linux. How can I put overlay networks on top of it? As soon as you have a cloud, you have your base infrastructure of network, and then you want to apply your application-specific network on top of it. And this is used by, there's this buzzword called network function virtualization. And what that is the traditional carrier companies used to have racks of redundant hardware. So if you went to AT&T and said, I want networking in your business, they pulled a Cisco box out and they put it in the rack for you. And then you upgraded your contract, they put a different box in. And you went away and they left that box there for the next customer. Well, this is really inefficient from the carrier point of view. So they said, can we take that, make it into a bunch of virtual services running on commodity hardware, just like if I go to Google Compute Platform and say, I want a database instance, they say, fine, here's your login, you have a database instance. Or I go to Azure Cloud and I say, I want a compute node of this size. They say, fine, I just provisioned you one of this size. They want to be able to do the same thing in networking. So network function virtualization is all about, can I take all these functions, run them in software, and clone them? And then on top of that, you need to provide an overlay network. And probably the most common one is VXLAN. VXLAN has multiple headers to put your packets together, and I'm running fast. So this is a common saying is basically any problem in computer science can be solved by another way of indirection. And in networking, we've discovered that any problem in networking can be solved by adding another header, except the problem of too many headers. So as soon as I wrote the VXLAN driver, the first reaction from Dave Miller was, what about MTU? Oh. So I'll whip through this, but basically, as soon as you add encapsulation, all the infrastructure components in the Linux networking stack that are there start to break. They don't break, but they just stop working for you. And so there's a lot of work being going into the networking stack to say, how can we do this and still keep that? The other one that happens is you've got companies that say, Linux networking stack works great at 1 gig. We can promise 1.5 million packets a second, no problem with the bridge or DP or Open vSwitch. But if you want to do a 10 gig software-based service, the Linux networking stack isn't fast enough. So Intel developed something called the Data Plane Development Kit. And what this is it's a library, almost like glibc, of poll mode drivers and infrastructure components that let you pull together the things to build a very specific app to solve these things. And all this works by basically, instead of running in the kernel, you pull all that out logic into your application. Now, this is great if you want to do like Brocade. We did the vRouter. Juniper has one. You want to do a load balancer in software. It doesn't work very well if you want to do a web server. So, but Cisco has taken this, built something called VPP that they had around, and spun it off in the Linux Foundation and the FDIO project. And this is an open source version of a router using DPDK with basically all the features you see in a commercial router. So, okay, this didn't sit this very well with the Linux kernel community. Well, why? Well, you're basically bypassing everything. So it came down to, there was a couple use cases that they wanted to solve without going the DPDK route. And the real main use cases is you want to do DDoS protection, like Cloudflare was doing, or you want to do internet independent location addressing, which kind of explained, but it's a whole nother talk. But basically it involves prepending headers, which is what Facebook is doing. And they wanted to do this at line rate. But user space networking was pretty much not general. Most of these DPDK solutions suck a CPU and have security issues because you're basically giving user space more permission than you want to. So they developed something called the XDP, Express Data Path. It's built using eBPF. It executes directly at the network driver. So as soon as a packet comes in, before anything else is done, it runs this code. And then it's generic. There's nothing specific about the network driver. What it's used for is two things. One, you can do the DDoS protection because you can say, I have a blacklist, I'll just drop those packets at line rate. Or you can modify the packets like the ILA does before the stack even sees them. And since this is at the very lowest level, it's very, very fast. The other one that's happening is Linux TCP started out with the original TCP versions around 2008. A bunch of researchers, and then I worked to get this into the kernel, did different versions of TCP to deal with how can I make TCP run fast on long-haul fast networks. So that happened. And now we discovered, as you see in buffer bloat, that especially in data centers, there's a whole lot of problems with, okay, this thing is chewing up all my switch bandwidth. And what happens is the sender's running at a certain rate, sending data. As the data goes down, it hits the bottleneck, backs up, and the receiver acts. And in TCP, you get these dynamics where as you increase the rate, you reach the point which is the rate of the system, and then you level out. And that's actually a good thing. But what happens with our current TCPs is the algorithms keep walking out farther and farther and farther using all the buffering. So you end up in the buffer bloat world, way over here on the right. And as you do that, you get the buffer bloat effect of your latency goes up and up and up and up. So there's two solutions to this problem that are being explored. The first one is the data center TCP, which has been done by Microsoft, Facebook, and a little bit of work with Google. And what they do is they use, instead of having the queue be just a dumb queue, they have a cutoff point, which is when you hit the cutoff point, they start marking packets with congestion experience bits. And they integrated that into TCP so that it basically keeps the queue small. And that gets 100 microseconds versus where they want to be 0 latency. And the newest one you may have heard of is TCP BBR. And what it does is it works to try to keep the optimum point, which is this knee right here. At this knee, you are at the optimum point of the network. You've got the most throughput and the least latency. To do that, it needs to understand the dynamics. And this is kind of one of those quantum effects where you can measure velocity and position, but not both at the same time. You can measure round trip time and you can measure bandwidth, but you can't measure both at the same time. If you try to measure bandwidth, to measure it effectively, you have to be over on this side of the curve. If you want to measure what the round trip time of the connection is, you have to be below capacity. So what TCP PBR does is it has mechanics to try to stay at this point. Then every 10 seconds, it walks out. It basically sends it a lower rate to get another estimation of round trip time. And then it intentionally goes faster than it thinks it needs to get an estimate of bandwidth. So it's kind of like it's driving down the road and every 10 seconds it twitches to see where the highway is. This is theoretically very well defined and everybody's appreciating the models. The part that still needs work is the fact that this is a different algorithm, and because it's a different algorithm, it has to play well in the universe of all the other algorithms. So the initial feedback we measured is that this is a little more aggressive than TCP cubic, so if two flows are sharing this connection somewhere, this may push the other one to get a slower rate. It's unfair. So we've got all these great ideas. We have a phenomenon we call protocol ossification. Protocol ossification is caused by the fact that all the commodity hardware out there is really old. If you look at your phone, it's running, Android phones runs 3.10 kernel. Well, 3.10 kernel is about 3 years old. And that's actually a fairly recent phone. If you actually look at the majority of Android phones, they're running things 5 years old or more. What does that mean? Well, that means that you can't do any of the newer TCP functions like TCP fast open or anything in your application. And this really impacts people like Facebook was the first one, and Google as well, where they're trying to run smarter client applications on older phones. So there's a proposal, which isn't gone through yet, called transport over TCP over UDP. And the idea is go ahead, use UDP because it's everywhere to move packets around the network, but put TCP on top of it and run the transport protocol in user space. This basically sucks the transport protocol into the application, but you can deploy the application on old phones. And what it does is it basically says, let's let just the application go to the network. You've seen this theme before, I think. And the main motivation here is TCP fast open because the TCP stack in Android and Windows kernels that you can't get anything up to date. So after rushing through all this, you think we don't have enough work? Well, there's some more things going on. First of all, there's work going on to put TLS, SSL, at least the transport part of it, in the kernel. And the reason behind that is there's things like multipath and other things where the security path kind of impacts other parts, and by getting it into the kernel, more control can be had. But the general thing that I've seen about this is in SSL, you also have a security handshake set up. So that will still be done in user space. It's only the actual encrypting of traffic that will be done in the kernel. And then the other part that's happening is there are more and more smarter NICs coming out. Mellanox is probably leading the way, but Intel also has it as well. And so there's a lot of work to take Linux kernel functionality that's in the networking stack and offload it to the hardware at higher rates. So traffic control, like QoS parameters, doing like the white box situation where you take the traffic control and move it into hardware. BPF, the Mellanox and Metronome cards both support doing BPF functionality in the card. And there's work on NF tables as well to do firewall in the network card. So I hope you like this rush through what's going on. And I was trying to leave enough room for questions. And I really want to credit Jonathan Corbett, who does LWN.net, for giving you the basics for this, and also the guys at the NetDev 1.2 in Tokyo who, if you want to know more about TCP PBR, there's a ACMQ article, or you can read the NetDev paper, and XTP has also got a paper at NetDev. So thank you.
Thank you so much for this very informative overview for the network. Now we have 10 minutes for questions. Okay.
Thanks for your talk. First question about TCP BBR. You said that it is some searching for optimum between minimizing bandwidth, maximizing bandwidth, and minimizing latency. And what is the what are coefficients? So so if bandwidth grows, how fast the value of the function,
Okay.
function
Okay.
grow? And
Let me give you a little background first. Traditionally, TCPs have been broken down into three subsets. There's one set that uses delay to control the window size. Another kind that uses another one that uses loss to control the window size. And this one is different in that they use pacing as a predominant way to control how fast they send, so they don't really use the window size. And they use the FQ module in the kernel. So basically, when it starts out, it says, I'm going to run at 10 megabits. And then it says, well, I sense that I could go up to this rate, and it stays at a certain rate. And then, like I said, every 10 seconds, it goes faster and slower. And obviously, if it can go faster it senses that the RTT isn't changing. It's, well, I've obviously got more capacity. I can go faster still, and it keeps growing. And likewise, if it senses that, oh, when I'm going faster, everything's getting slower, I should slow back down. So it's kind of a combination between the loss and the delay based, but it's done using pacing instead of using window size.
I guess Wi-Fi rate choice works the same.
Yeah, it's kind of like, I guess it's on the same theoretical basis.
Okay. And the second question, do you really like TCP over UDP?
I don't like it, and I'm not a big fan of Quick either, but I can understand the problem the people developing applications have in the mobile space. They want to have the best service to the customers, and they're stuck with the infrastructure they're given.
Thank you. Next questions. Вопросы по-русски? Looks that okay.
You've said on the beginning of the talk that if you want to change the core network API, you have to also cover all the existing driver base. So is it frequently changing, or is it more of adding new features and not changing the old stuff?
It's mostly it's been changing new features after we did a few core changes in 2.6. The biggest change that happened was obviously when we went to multi-queue devices, we had to change the APIs for multi-queue. And a lot of times we'll change the API for something. The most recent one I can think of is how network buffers can be recycled. And we would change it in the 10 gig drivers where it mattered, but nobody would go bother. We'd leave the same API around for all the slower drivers to just use that.
Oh, okay, thanks. And are there any like maybe mathematical or some other investigations in alternatives to TCP and UDP, like some new way to transfer data which is not yet fully covered by all the use cases?
A lot of people are doing that, but they're doing it they kind of avoid doing it at the transport layer. They do it at the application layer. So people that do like forward error correction encoding and stuff. But then a lot of that works. I mean, the way the transport protocols is we have a well-defined sockets API, and we have semantics about that API, and a lot of the constraints are because of that API. And once you go into the application, you can say, well, I'm doing movies, and I know a movie looks like this, and I don't really care about the buffering, but maybe I care more about window framing for my movie. So I should make my protocol work on that. So by using application semantics, you have different than socket semantics, you can get some advantages.
Okay, and do you think it's possible with all the fuss around the quantum computing to have some form of quantum networking?
I hate to say yes, but I hate to say no. It's just, I don't understand.
Okay, thanks.
Thank you. Next questions. Okay, probably one from me. For this white box approach with commodity hardware, do you observe the usage of TCP offload to the hardware, or no? Or it's just a service-based?
Most of this hardware doesn't support that kind of thing yet. Most of this hardware is basically talking about really big, fast switches and TCAMs and stuff like that. They aren't servers. They aren't endpoint. They're more intermediate gateway systems. But some of the other, the Mellanox cards and so like that, they aren't so much doing TCP offload as they're trying to do what functions can we do before we get to TCP.
Thank you. Еще вопросы? Okay, think that thank you very much once again. We'll have a short break for 10 minutes before next presentation. Thank you.